Okay, what are the rules that we're going to follow? Well, here, let's start with looking at a typical basic sorting problem. Say a university has student records. And for every student, there's a certain amount of information. Maybe there's a class number, there's a grade, there's a phone number, maybe an address. So we refer to an item as a record, or the information that we're going to sort. But in particular, there's a piece of a record called a key. And what we want to do is put the records into order according to the key. That's the sort problem. Rearrange an array of n items into ascending order according to a defined key, which is part of the item. Now, our goal is to be able to sort any type of data. So let's look at a couple of client programs. First example is to just sort some random real numbers into ascending order. So here's a client that calls our insertion sort method. And all it does is read numbers from standard input, then into an array A, then calls insertion sort, and then prints them out. And you can see on the right that the numbers are printed out in sorted order. This seems like an artificial kind of input, but actually we'll look at an application even in this lecture. And there are many applications where random inputs are a fine model. Here's maybe a more familiar sort client that sorts strings. And in this case, it reads the strings from a file using our read strings method in our in class, which takes a file as argument. So we take the file name as the first command line argument, read in an array of strings from that file separated by blanks, call our insertion sort method again. So insertion.sort is a method that takes an array A as its parameter and it as its first argument, and it rearranges the strings in that array to be in sorted order. So in this case, words3.text has a certain number of three-letter words, and this client program will result in those three-letter words being rearranged into alphabetical order. Here's another client that we could use our sort program for if we achieve the goal of sorting any type of data. In this one, we're going to sort the file names in a given directory. So again, we use the file class from Java, and we go and use the list files method from that class to get an array that contains all the file names in the given directory. And that's an array with file names in it, and insertion sort takes that array as its first argument, and again sorts them, and then we go ahead and go through them one by one and print them out, and they come out in order of file name. So that's three different clients, three completely different types of data. And the first rule of the game that we have to think about is, how can we make it so that we can implement one sort program that can be used by these three different clients to implement three different types of data? And the way that that happens is a mechanism known as a callback. So that's our basic question. How can sort know how to compare data of all these different types without being given any information about the type of an item's key? And the answer is that we set up a mechanism known as a callback, or a reference to executable code, where the client, by passing an array of objects to the sort function, in Java, there's an implicit mechanism that says that any such array of objects is going to have a compare to method. Then the sort function calls back the compare to method associated with the objects in the array whenever it needs to compare two items. There's a lot of different ways to implement callbacks, and that's programming language specific. Different languages have different mechanisms. It's all about the idea of passing functions as arguments to other functions, which is a deep area that gets us into functional programming and thinking all the way back to Turing and Church. For Java, because of the desire to check types at compile time, they use a specific method called an interface. And we'll look at the details of how to implement callbacks with Java interfaces now. It's a little bit of programming language detail, but it's really worthwhile because it allows us to use the sorts that we develop for any type of data in a type-safe manner. So we already looked at some clients. This is the example of the client program that sorts the files in a given directory by file name. So it just calls our sort method with an array of some type of object as first argument. Now, built into Java is the so-called comparable interface. And all the comparable interface is a specification that a data type that implements comparable will have a compare to method. And it's generic, it'll be compared to against a certain type of item. Now, when we implement objects that are to be sorted, we'll implement the comparable method. That's up in the top. Class file implements comparable file. And since sorting is an operation that's used in so many situations, many of the standard Java types that you would expect to involve sorts will implement comparable. And all that means is that that data type has an instance method that will implement the compare to method. It'll compare this object against the object given as argument, and depending on some complicated test, it'll return -1 meaning less, +1 meaning greater, or 0 meaning equal. Now that compare to method is really all that the sort implementation needs. First, it says that it's going to take as argument an array of type comparable. So that means the objects in the array are going to implement the comparable interface, or that they'll have a compare to method. And then the sort code can just use that compare to method invoked on an instance of the object like an entry in the array, and as argument another instance in the object like another entry in the array, to test whether the first is less than the second, as in this example. The key point is that the sort implementation has no dependence on the type of data. That's handled by the comparable interface. And a different comparable array will be sorted in the same way. They'll eventually, because of the interface mechanism, be a call back to the actual compare to code that goes with the type of object being sorted. Now, there's a few rules in there, natural rules, but they're worth talking about and paying attention to, that the compare to method has to implement. And it's so-called a total order. And all that's saying is really that it must be possible to put items in order in a sort. So there's three properties. First one says that if v is less than or equal to w and w is less than or equal to v, then the only way for that to be true is if they're equal. And then there's transitivity. If v is less than w, w is less than x, then v must be less than or equal to x. And totality is that either v is less than or equal to w, or w is less than or equal to v, or both, they're equal. And there's plenty of natural total orders in the types of data that we normally want to consider for sort keys, like integers or natural numbers or real numbers, or alphabetical order for strings, chronological order for dates or times, and so forth. The cartoon on the right shows that not all orders are necessarily total orders. So rock, paper, scissors is intransitive. If you know that v is less than w, w is less than v, you don't know that v is less than or equal to v. I'm sorry, v is less than w, w is less than or equal to x, then you don't necessarily know that v is less than or equal to x. All right, so the comparable API, then by convention in Java, we always need to implement compare to such that v.compare to w is a total order. And also by convention, it returns a negative integer if it's less, 0 if it's equal, positive if it's greater. If this object's greater than the object given as argument. If the types are incompatible, or if either one is null, compare to should throw an exception. Now, again, many of Java's standard types for numbers and dates and file and so forth implement compare to by convention. Now, if we're going to implement our own type, then we have to go ahead and implement the comparable interface according to these rules. And usually that's fairly straightforward. So here's an example. It's a simplified version of the date class that's implemented within Java, just to show the idea of implementing comparable. So after the class declaration, we write implements comparable, and then we fill in the generic with the same type because we're only going to compare dates to other dates. In this implementation, the date class has 3 instance variables: the month, the day, and the year. And the constructor fills those in from the arguments, as you can see. So now if you want to compare 2 different dates, then the first thing to do is to check if this year is less than that year, and where that is the year given, the date given in the argument. If that's true, then it's less, return -1. And if the year is greater, return +1. Otherwise, the years must be equal, so we have to look at the months to do the compare, and so forth down to do the days. Only if they're all equal do we return 0. So that's an example of an implementation of comparable by implementing the compare to method to put dates in order, as you might expect. So the Java language helps us with this comparable mechanism so that we can sort data of any type. But when we come to implement sorting algorithms, we're actually even going to hide that beneath our own implementations so that our sorting algorithms actually, the actual code, can be used to implement sorting in many other languages. And the way we do that is to take the 2 primary operations, compares and exchanges, that we use to refer to data and encapsulate them just as static methods. So we're going to use a method less that takes 2 comparable objects as arguments, and it just returns v.compare to w less than 0. And then the other thing that we do when we sort items that are in an array is to swap or exchange the item at a given index I with the one at a given index j. And that's every programmer's first introduction to assignment statements. We save a of I in a variable swap, put a of j in a of I, and then put swap back in a of j. So now our sort methods to refer to data will just use these 2 static methods. And there's a good reason for that. Here's an example. Suppose we want to test if an array is sorted. So this is a static method that is supposed to return true if the array is sorted and false if it's not. And all it does is just go through the array from 1 to the length of the array and test if each item is less than the one before it. If you have an item that's less than the one before it, then it's not sorted, you return false. If you get all the way through the array without that happening, then you say the array is true. That's pretty simple code. The question is, if you have a sorting algorithm that passes that test, are you sure that it correctly sorted the array? Well, the answer to that question is yes, if you used only the less than exchange methods to implement, to refer to data. Because then you know, because you use the exchange method, that the data in the array after the sort is the same data as was in the array before the sort. If you have a sort method that can store any values in an array, it could, for example, store zeros in every array entry. That method would pass this test, but it didn't really correctly sort the array because it overwrote all the values. So we use less than exchange to be sure that we can test that our methods work with a method like this.